So, good morning everyone. My name is Jackie Craig and I'm the moderator for this session. I'm absolutely delighted to be working with this emergency management panel discussion. My background is in defence science. I was a defence scientist for 36 years, so I'm quite used to taking science and technology and adapting it and using it to solve difficult problems, and emergency management falls right into that bucket. I also happen to be a volunteer with the State Emergency Service, 8 years now, and I've deployed 4 times into disaster areas, once into the Kangaroo Island fires and 3 times into a flood zone. And probably to you all, the name of Lismore will be very, very prominent in your mind. I deployed to Lismore, and it was whilst I was there, I recognised within myself the importance that space data and space capabilities could bring to improving emergency management across all of the phases of emergency management. Now, traditionally, emergency management is categorised. It's categorised into 3 phases, known as prepare for the event, respond to the event, and recover from the event. In all of those 3 phases, the ability to make good operational decisions is absolutely vital. It's vital so that you can properly use your resources, know what resources you need, triage what you need to do, and basically just be overall effective. But of course, as everybody here will know, good operational decisions are really underpinned by accurate and timely information. Information derived from space-based centres can play a critical role in decision support. They can provide what we would call actionable intelligence, including things like improved situational awareness and warning and indicators. Today, for this discussion, we welcome an excellent panel with a deep collective experience in the generation and use of space-derived data across the prepare and respond phases. And that's how we're actually going to run this panel today. Each of the panel members will come up and give a talk. There are 4 panel members. The first person to give a talk will be Anthony Rea. Anthony is the principal at Meteorite Consulting, and he will discuss his work in providing vital weather prediction during the prepare phase, which allows people within the incident management team to figure out ahead of time the types of things that might happen, the types of situations they might be dealing with, and actually prepare for that. The second person to talk will move into what we call the response phase, and that is providing information during the actual event, so it has to be real time, it has to be highly accurate. And for that, I will be introducing Craig Earl-Spurr. Craig is a senior meteorologist in the BOM, which is the Bureau of Meteorology, and he specialises in tropical cyclones. He'll lead us through how he provided real-time information during the response phase. Now, as you'll be aware, when you're working within an IMT, you're not just working with one data source, you're working with a number of data sources that need to be brought together to provide that actionable intelligence that will support your decision making. So the third speaker will be discussing that in the response phase yet again, and that is Juan Ossa-Morena, and he will discuss his work in integrating various data sources to provide situational awareness. And finally, last but not least, and perhaps the most important person on the panel, is Sue Streit, the person who actually makes the decisions. And so we will be shifting gear with Sue's talk from talking about the science and how the data is produced into how it's actually being used. And Sue will lead us through the types of challenges that the incident management team face and how data can help in that scenario. So to kick off, we'll invite Anthony Rea to the platform to give his talk, and I'll just give you a brief summary of Anthony's experience. He's currently the principal of Meteorite Global Consulting. He is an internationally recognised expert in Earth observation and international data exchange, utilisation and policy, and I can't emphasise enough how important that role is. From 2019 to 2023, he was the Director of the Infrastructure Department at the World Meteorological Organization. So as you can see, an excellent person we've managed to capture to be part of our panel, and I would like you all to welcome Anthony to the stage. Thank you, Anthony.
Well, thanks very much, Jackie, and good morning, everyone. I can just make you out. Firstly, I'm not presenting my work, I'm presenting the work of the World Meteorological Organization and the Bureau of Meteorology and all of the other national Met services. But what I would like to put to you is that preparation doesn't start when we see a tropical cyclone on our weather map, or when we pick it up on the weather radar, or we see it on the satellite. It starts well before that, and in the case of weather prediction, it starts with setting up the global observing systems and the global processing systems and the global frameworks and policies, as Jackie mentioned, that enable this to happen. In fact, billions of dollars of global infrastructure which is involved in creating weather predictions. So we've got kind of what I would say is there's two paradigms of satellite product generation, generalisation, but anyway, let's say there's two paradigms. One would be a vertically integrated approach where we take a satellite system, we run it through some kind we take a satellite observation, we run it through some kind of product generation system, and finally we do some calibration validation, and then we deliver a product. So it's a kind of what we call a stovepiped model. It's a very appropriate model if you're generating something like a physical parameter, like measuring sea surface temperature, or maybe you're looking at algal blooms or something like that. Weather prediction globally tends to work a little differently, what I'd call a horizontally integrated approach, and that's where we would have satellite sensors, in situ observations. We run those through a data assimilation scheme into a physical model, and then use that to generate products that are then used for downstream use and to support decision making downstream. The global observing system for weather is complex, and the model that's taken, the model that's used, the organisational model is give us as much data as you can and we'll assimilate it into the models, we'll find a way to do that. So this kind of conceptually describes how that happens. So we have geostationary satellites in a kind of a ring around the equator, which are always steering at the same place on the Earth, and we use that rapid repeat time to watch rapidly changing phenomena. We have polar orbiting satellites, much lower, closer to the Earth, 700, 800 kilometres. By virtue of being closer to the Earth, they can have higher resolution sensors, which enable us to take measurements of the atmosphere. And we couple those with things like measurements from aircraft, weather balloons, automatic weather stations, drifting buoys, ships, and so on. So any data that's available that can be used to measure the weather is taken into these models. And a good example of that is GPS satellites, where the noise from the GPS observations, the delay in the GPS signals as they come through the atmosphere due to atmospheric moisture can be used also to feed into those weather models. So I don't know whether anyone would want to have a guess how many satellites the Bureau of Meteorology uses in its operational weather forecasting. It's really quite a huge number. It's over 20 instruments, over 17 satellites. So there are microwave sounders that look at actually the radiation that's emitting from the air itself. So these are really, really faint signals, and this is why we need polar orbiting satellites to take these measurements. So microwave sounders operated by the European Union as well as the US. Hyperspectral infrared sounders, once again looking at that kind of profile of the atmosphere, the temperature and the moisture of the atmosphere, operated by Europe, operated by the US. Microwave images, looking at slightly higher resolution but still in the microwave, operated by, in this case, JAXA, the GCOM-W satellite. The infrared imager, for those of you who've seen the satellite images on the Bureau website, these come from the Himawari 9 satellite operated by the Japan Meteorological Agency. There are scatterometers which look at the ocean surface and can pick up the wind right at the ocean surface, picking up the diffraction of different wavelengths by the waves on the ocean surface. And finally, we have atmospheric motion vectors. I mentioned that geostationary ring of satellites around the Earth. So all of those satellites are monitoring in real time and basically tracking clouds to create measurements of wind that can then be fed into the models. Finally, I mentioned GNSS radio occultation. So there's a range of satellites there operated by the US, by Europe, by China, by Germany, and by Korea and Spain as well. So there's a kind of what we'd call maybe a poor person's constellation of satellites used in that area. Plus, as I already mentioned, automatic weather stations, weather balloons, aircraft, ships and buoys, and measurements of sea surface temperature. This is a quick example. It's actually quite an old example, but what it gives you a picture of is each one of these panels is a different observation type that's going into the Bureau's weather models. I think this example is at least 5 or 6 years old, maybe longer. But you can see there, maybe the middle panels there, you can see polar orbiting satellites creating a swath across the Earth. In the top right, you can see global coverage from these geostationary satellites. In the top left, you can see aircraft observations, and down below, in the top bottom right, you can see ships and buoys and those types of things. So there's a huge global cooperation that is needed to create these observations and feed into the models, which I'll then talk about. So the Bureau runs a few models that are used in weather prediction. There's ACCESS-G, which is the global model. It has a resolution of about 12 kilometres, runs 4 times a day, and this provides forecasts out to like 7 to 10 days. It's running on pretty big supercomputing infrastructure, 1.6 petaflop machines, 4 petaflop machines. So these are huge supercomputers, maybe not the biggest in Australia, but amongst the biggest in Australia. The point I'll make is that this is really robust operational infrastructure that's running all the time, every day, generating the weather forecasts that you use in your daily life, also providing services to aviation and other sectors, agriculture, etc. But when a tropical cyclone comes, 12-kilometre resolution is a little bit coarse to pick up the eye of a cyclone. The eye of Cyclone Alfred was something like 30, 40 kilometres across when it was Category 3, Category 4. So the Bureau spins up within the global model, nested within that, it spins up what's called ACCESS-TC, a tropical cyclone module, and this is like a little subset at a high resolution that sits within the global model and kind of tracks the cyclone as it moves. So this is at 4-kilometre resolution, so it enables a greater kind of accuracy in terms of picking up the depth of the depression at the centre of the cyclone, which drives its intensity, and this is used operationally in generating the tropical cyclone tracks that are then used by the Bureau forecasters in the generation of their forecasts. And we will move over to Craig Earl-Spurr in a minute, who is one of those operational forecasters who'll talk about how they do that. So, Jackie, I think I'll stop there. What I'm trying to get across is that this is global infrastructure that's there all the time. It takes a lot of planning. It takes a lot of investment. There's replacement cycles for supercomputers. There's replacement cycles for the satellites that are on orbit. This all needs to be nationally and globally coordinated, which is the role of the World Meteorological Organization. So, thank you. I'll hand back to you, Jackie.
Thanks for that, Anthony, and I noticed you did manage to move the microphones up to your level, and I've now had to move them back down to my level. So next, I'm delighted to welcome Craig Earl-Spurr, who is a senior meteorologist for the BOM. Craig has been an operational meteorologist for the BOM since 2011, and since 2021 he's been a senior meteorologist in the Bureau Tropical Cyclone team, which monitors tropical cyclone development all the way from the Indian Ocean to the Coral Sea, so it's an absolutely massive job. Craig is joining us today virtually, so I'm hoping he's up there on the screen somewhere after I disappear. So over to you, Craig.
Thank you, Jackie. Can you hear me okay?
Yes, we can, Craig.
Okay, and I've got a share screen of a couple of slides that hopefully is up. Yeah, so the whole tropical cyclone warning stage, we start really with the prediction models that Anthony's just gone through. They're normally giving us the earliest indication of a tropical cyclone developing. But then as the event unfolds, the satellite data really plays a crucial role in monitoring the development of any cyclone. I've got a few examples that I'll bring up shortly, but the satellite data, it's absolutely crucial for us. Tropical cyclones all form out over sea and often a long way away from the coast. So without any weather stations out there and very sparse buoy observations, we rely on the satellites to provide the spatial coverage that we need to be able to accurately observe these cyclones as they get going. And since the advent of the weather satellite era 50 odd years ago, the accuracy of observing these has just gone up and up. And I believe at the time, back in the 70s, they had no idea how many cyclones were actually occurring until they started to observe them on satellite. In regards to tropical cyclone Alfred, sorry, I'm just having a bit of trouble getting my slide to move forward. So I've got a couple of examples here. On the left is what people are probably a bit more familiar with. This is from the Himawari geostationary satellite. This is the visible channel. We can see Alfred, not quite the classic cyclone pattern, which I'll talk a bit more about in a moment. But I've overlaid the radar image, which is really only capturing the western half of Alfred as it's approaching the coast. This is from March 5th, when we're already starting to observe some pretty heavy rainfall across northern New South Wales and southeast Queensland. But we're not really seeing even half of what this cyclone's producing at the time. The image on the right is from one of our polar orbiting satellites. This is one of those microwave channels that Anthony mentioned. And this one in particular, it helps show where we've got the really deep thunderstorm clouds that aren't quite as obvious on the visible imagery. And so the heaviest rainfall at this stage is really on that southern side and still well offshore. So when we're already seeing heavy rainfall at this stage, we know that there's still plenty more to come and potentially getting a lot heavier. Another part that's really critical about this, I'm sure everyone's aware that an unusual feature of Alfred was the way that it moved much further south than tropical cyclones typically do. And as they move this far south, they tend to lose the classic tropical cyclone structure with that really distinct eye and the strong winds and rain associated with them being more or less symmetrical around the centre. And in fact, we start to see the rainfall being concentrated on the southern side much more, as is the case in this event. But also the wind becomes far less symmetrical. And once again, particularly Coral Sea, Tasman Sea, it's that southern side where we get the greatest concerns of the strongest winds. And that leads me on to my next slide, which this is, again, the polar orbiting satellite. This is the scatterometry, which is showing us an estimation of the wind field based on sampling the capillary waves. So it's not the big waves being generated by the winds, it's the little ripples on the surface that gives us these estimations. And we can see in particularly the yellow, and it kind of graduates to an orangey red colour on the southern side is where we've got our strongest winds. I've labelled on the very top of the image Cato Island, and on the very bottom, Lord Howe Island. So these are the two nearest offshore observation sites we have. Cato Island had actually stopped reporting after Alfred had already passed by and caused a bit of hectic weather there. And Lord Howe Island is too far off to the south, indicating only 29 knots, whereas we're seeing 50 knot winds being generated. So this is kind of giving us that confirmation that it's matching what we'd expect to see of a tropical cyclone moving this far south. But we also see place a rather large arrow on top of that wind display. And that arrow is roughly parallel to the direction that Alfred was moving at this stage, which becomes really important for the wave generation. We've got a large area of winds that are in the same or blowing in the same direction as that movement, and they are amongst some of the strongest winds being generated. And this is the really prime conditions for large swells to also develop. And we observed these. They started on this 5th of March and continued for a few more days, with the largest swells probably a day or two later. So being able to monitor this stuff in real time, we wouldn't be able to do it without the satellite data, but it firstly confirms that we're kind of on track more or less with our forecast, or we can make adjustments and fine tune as we go and update the information that we're handing on to the emergency services and the Australian public more broadly. And I'll leave it at that. Thanks, Jackie.
Yeah, thank you, Craig. It takes me a while to get from my seat on the floor up to the stage, so an excellent talk. It makes me realise just how much people rely on the guys that predict the weather. I'm a mountaineer. I go into really, really remote places, and I can tell you I spend a lot of time looking at weather forecasts, and I'm sure many, many times you guys have stopped me getting into some dreadful trouble, so thank you very much. We're staying in the response phase, and now we're moving into understanding, bringing together disparate sources of information to provide actionable intelligence, and Juan is going to be the person that will lead us through what he does in that area. Juan is a flood risk specialist with over 10 years of experience in research, consulting, and startup environments. He's currently the senior engineer and account manager at Floodmapp, where he drives customer success and business development, working with government, insurance, and utility sectors. And I really love this about Juan's bio, the fact that he's using the science and he's demonstrating very clearly that he wants that science to have impact. He has deep technical expertise and is passionate about identifying how real-time flood intelligence can improve emergency response and disaster resilience. So please welcome Juan to the stage.
Good morning, everyone, and thank you very much for attending this panel, and thank you very much for the Andy Thomas Space Foundation for the invitation to Floodmapp to share how Floodmapp is working with emergency managers. So I'd like to start with the why. Why do we do this at Floodmapp? And these are what you see in the slides are a couple of messages that we get from emergency managers in the US, in Australia, and in New Zealand, where we operate. And basically, this summarizes very well the challenge that we have ahead, which is we have very good point information, but when we work in emergency management, we need to evacuate towns and cities, and just one point is not enough. We need to have like full spatial extent of these events. Sometimes we also have very good flood models that allows emergency managers understanding what is the catchment response to specific events. But we need to have situational awareness. Those flood models are usually like predefined scenarios, and we need to have real-time information of what's happening with the event that we want to respond to. So this is the challenge that we have. How can we have like spatial but also temporal with frequency that allows us to understand through flood intelligence what can we do to minimize the negative consequences of floods. What you see here is some of what Floodmapp was producing for Tropical Cyclone Alfred, the Southeast Queensland, Northeast New South Wales in early March this year. How we operate is basically that we merge different sources of data, and that of course includes space information, space data, both space imagery or space SAR, with ground information plus alternative sources of data. We merge all of this so that we can generate live maps that are updated every hour so that emergency managers know what's happening in their catchment and what's going to happen over the next hours. In blue, what you see there in blue are the maps showing what was the extent at that time for Tropical Cyclone Alfred in Southeast Queensland, Northeast New South Wales. And then in colors, you see how you can then post-process that information to get more intelligence for emergency managers. So in colors, there are some lines. Those were the roads that were affected, and the color shows the severity of the flood in those roads. And you can do the same. Instead of roads, you can use these to track the impacts to power substations, to schools, to police stations, to residences, to anything that you have that is of interest. Now, we're of course in a space event, so how does space data comes into play here? So what you see in this slide is an example for Shepparton in Victoria in 2022 for the big floods in October 2022. So on the left-hand side of the screen, you'll see the final output of Floodmapp, which basically we start by taking point data, gauges from the Bureau of Meteorology and from the similar agencies in the US and New Zealand. We transform that into live maps, and then we benchmark and assess the quality based on many other sources like traffic cameras, aerial imagery, flood studies, and of course, space data. And this is an example how Sentinel-2 imagery was showing that same event in Victoria in Shepparton. So there's a very good overlap of both images, and what you see from the satellite, it looks great, it looks amazing. It's very useful for you to have an idea of what was happening at that point in time. But then the challenge becomes, okay, is it possible to have such an image from a satellite source every hour? And then unfortunately the answer is no, because if it was the case, then I guess we could use satellites all the time. But of course there is a time in between satellite observations that there is no information. And also there are some other challenges like clouds, or when it's during the night, you will not have access to imagery from satellites. So what I want to highlight here is that the best approach to have found to be able to use space information is to merge that with ground data so that we can produce a product that is highly accurate on a spatial scale, but is also like reliable on temporal scale, and we can have constant updates of information every hour. In this slide, you will also see another source of data which is very useful, satellite SAR. So because it's radar data, it can penetrate clouds. It's very useful when it's very cloudy, which is of course very often during floods. And it can also work during the night. That's very, very useful. So it shows in red, like the image in the left, how SAR, satellite data, gives an idea of how this flood in Gympie in 2022, this is also for the 2022 event, but this time it's in Queensland, in Gympie, gives a decent idea of the event. Then we'll see imagery, lots of clouds, so it's really blocked. And then on the right-hand side of the slide in yellow, we see how a final output of different sources, including SAR, including ground gauges, and other sources that help us benchmarking the final output, allows us to give like the best representation in real time of what's happening in every catchment. And again, this is updated every hour, so the emergency managers have full situational awareness. Oops. Now, the next example that I want to show, this was for Targominda in Queensland in 2025, early in April. Again, in dark blue, we see satellite information, satellite imagery at that specific time, and it's very useful because this is like an observation of what's effectively happening. Then in light blue, you see what was the merge, like the final output of Floodmapp products, how that's showing the event at the same time as the satellite observation, and there is a very good agreement again. But then that was not the critical time in that town. So in red, what you see there is what we were able to generate a couple of hours later in that event, and we can see that the peak conditions were more critical than what the satellite capture showed us. So again, the key message is, again, we like to merge different sources to get the best final output. Then after that, I would like to highlight some of the key things that you can get when you use multiple sources of data, and is that after mapping and having like that real-time situational awareness, you can also provide very useful information on roads, on power substations, schools, police stations, and many more, so that the users can have a good idea of what are the impacts of those events. So what you saw there was basically how after getting the maps, we're able to identify what roads and send that information to the users so that they have a very good idea of what roads and to what extent they're being impacted by an event. There's still a little bit of human involvement, but we look forward to, like, in the future, to be able to have this fully deployed automatically so that you can merge multiple data sets, including space data, in the best possible way so that we can minimize the negative consequences of floods in communities. Thank you very much.
Thanks for that, Juan. It was great to see the real products that you're producing that helps people make their decisions. So the next speaker is Sue Streit. Sue is with the Queensland Police Service and is a principal planner in the Queensland State Coordination Centre. Sue will lead us through the types of challenges that people face when responding to emergencies and the types of decisions that they have to make and how data can help. Sue is exactly the kind of person that you would want to have in an incident management team. She was a logistics officer in the Australian Army for 30 years. Her passion for emergency management was sparked during the Queensland 2019 cyclone, during which time she was the defence liaison to the Queensland state, so she has real deep experience in dealing with disaster management. She also has very well developed skills in coordination, logistics, leadership and strategic planning. So I'm really looking forward to hearing what Sue has to tell us. So please welcome Sue to the stage.
Thank you very much for having me today. I'm very pleased to be here. I know we're talking about TC Alfred, but just to understand what we do, I've chosen to do the first 5 months of this year in 2025, just to give you a better understanding of how disaster management in Queensland works. What a start it was. 48 days of activation in total, North Queensland, Tropical Cyclone Alfred and Western Queensland. There were 3 water-based events, but they were all totally different. But they're all slightly linked, each with its own challenges. And it cost Queensland, in the end, over $2 billion. So starting at the beginning, North Queensland, this was a rain event with a record-breaking 1,777 millimetres in 48 hours. Yes, 1.7 metres of water. Townsville exceeded its yearly rainfall record by March. In this event, the BOM, as we heard before, provided the critical early warnings using their suite of tools which allowed us the situational awareness we required to be able to prepare for the event. During the event, we transported 800 local and interstate SES, as well as Queensland Police and the Queensland Fire Department, specifically the Swiftwater Rescue, before, during and after the event. Infrastructure, highways and the Gregory Development Road are significant supply routes for North Queensland, and they were cut in multiple locations and in some cases over multiple times during the event. Alira Creek Bridge, which is the one here, was damaged with a section missing and live power swinging between. This became a focal point with the ADF, Department of Roads, Department of Rail and Energy Queensland working together, firstly to get workers into Ingham, secondly to erect a temporary military bridge that allowed 287 supply and support assets, mostly vehicles, to be individually escorted, so they literally walked them over this dodgy little bridge for the event. What made this more impressive is that this was done in 6-hour windows. So because the bridge was removed every night so that Queensland Roads could work on the repairs of the bridge underneath each night, 9 days it took them to repair that bridge and make it usable. Very impressive. Critical infrastructure in Ingham includes power and communication. They were all out for a significant amount of time during this event. Firstly with the substation, which you can see there, which definitely went underwater, but at the beginning of this we were able to sit down and go through our GIS and the data that we had with just enough time to prepare the facility in advance so that hopefully we could reduce the damage and therefore reduce the time it took to return it to power. At the same time in Townsville, the Ross River Dam was increased by 48% in just 24 hours, bringing the dam up to 167% with its gates open. So it's a phenomenal amount of water. This prompted the evacuation of the black zone in Townsville, which I don't know if any of you are from Townsville, but it's a significant evacuation. This is all done in advance with the technologies and the data that was previously provided in these presentations. Just quickly, there were 2 deaths, unfortunately, and we are still dealing with the outbreak of melloidosis, which is directly related to the event. And 34 people have died since. Okay, the most important one, TC Alfred. So the State Disaster Coordination Centre activated on the 2nd of March and exercise TC Alfred crossed on the 8th of March after a little bit of dancing that it did. In this event, we had plenty of warning, which is generally good, but this also comes with its own issues, including staff fatigue, especially when it was on the back of the North Queensland event. This event was complicated with 8 districts and 13 local disaster management groups, so a broad section of Brisbane itself being involved. Each had its own unique problems, geography, demographics and building standards, interestingly. To make it even more complex, almost all of the emergency workers and all the staff from the State Disaster Coordination Centre lived in the impacted area. Some staff couldn't make it to work and some had significant damage to their homes as part of the event. And yes, that tree hit our building. It was very, very loud. Communication and power were again a significant issue, but this time it was the scale. At the peak, we had 350,000 people without power in Brisbane, the largest outage in Queensland history, but it wasn't one substation. It was hundreds of downed lines, damaged facilities and safety hazards. So I take my hat off to the energy people who were able to bring it back. And as you would all know, modern communications only work for so long as we have power. So there were a lot of people in Brisbane who didn't have TV, radio, news, or most importantly, warnings. Okay. Western Queensland. This was huge. The impact area was 3 million square kilometres, a total area greater than that of Victoria. Not only in size, but we broke records in depth, with many of the towns experiencing flood levels that no one had anticipated. The limited ability to predict this event in the West was not just from the lack of radar in those areas, but also the limited data that we had, the modelling and imagery. This is the stuff we need to understand the situation to be able to help. In this particular example, Floodmapp were amazing with the limited information we were able to give them to produce what they did for us. Something as simple as gauges causes major concerns. Many of the automatic ones were damaged or even washed away during the event. Water levels exceeded the manual levels, so locals got creative and made some of their own gauges, like this one in Thargomindah. Like most events, they had issues with resupply power and communications. Of particular interest was the use of the satellite communications. So going back to the gauges for a moment, some of the towns designed their own gauges, obviously prior to the event, and built them with satellite communication due to the unreliable nature of the traditional communication in the outback. However, satellite solutions come with some of its own problems for us. At the moment, Queensland currently, their emergency warning system cannot push warnings to those devices. This is a major issue, and it makes tourists in these areas, such as the grey nomads, particularly vulnerable. Sticking with the unique nature of Western Queensland, a particular focus for this event was fences, something a bit different. Not just property fences, but fences for feral animals. There were thousands of kilometres of them. Trying to identify the areas which were damaged or affected is critical to protecting the livestock and ultimately the livelihood of the farmers. Satellite imagery was and could be even more very, very useful here. Another quite unique vulnerability in Western Queensland was for food for those dispersed livestock, which can be spread over enormous properties. A request for assistance was submitted, but we found it incredibly difficult to try and identify where those livestock might be congregating. Again, imagery, short notice imagery of this would be amazing. Other requests for assistance were for rescues. Trying to get to them can be a mammoth task in these remote areas. There aren't many aircraft that can fly that far and land on postage stamps, for those of you who know what they are, and return without refuelling. The different types of fuel and the difficulty positioning it in these remote communities adds to the complexities of these problems. So in conclusion, that's just a really quick understanding of how we deal, or what some of the things that we have to deal with during an event, and some of the things that we would like to see to make it a little bit easier for us in the future. Thanks very much.
Okay, so after those four very insightful talks, I'd like to invite the panel members up onto the stage to answer any questions. So are there any questions from the audience to start off with?
My one's probably more for the prepare and respond, but also assist with the recovery. How does the communication between government departments, satellite technology, talking about weather events with water levels to get predictions and bits and pieces, but also internationally with communication between countries for satellite imagery and everything as well, and then even at a smaller level in between different states and things, how does, or is the communication between these entities, government departments, countries, is that working well enough, or what needs to be done to increase the speed, I guess, of decision making and information?
I guess everybody's looking at you, Sue.
Hopefully that's on. It is something that we need to work on. Look, we have mechanisms through the National Emergency Management Australia, the NEMA, who control some of the contracts that we do use, which is probably a massive improvement in what we do. Across states, I think we have a long way to go in how much communication we have, and it's part of what I'm trying to do within the planning organisation within the State Disaster Centre in Queensland is talk to them more, which is trying to get out, which is quite hard. I think in Queensland as a state by itself, understanding that we have a very unusual setup in Queensland where the local areas control most of the disasters. It's not run by the state. So we're there to help when it's out of their control. So they have a lot of connections and contracts, and like with Floodmapp, for example, with those local government areas, that is an area I think that we definitely need to improve in that communication about what they're using and how they're using it. Does that sort of answer that question?
I would also like to complement that by saying that during an event, it's also very important to try to build resilience by having multiple sources of data available. So you have some providers of satellite information. There are some private providers. There are also like Sentinel and other like government providers, and you know like more or less when those satellites are passing next to your areas of interest. So it's key to have that very clear, and also like to know what other sources you could use. So there are traffic cameras. Many of these areas have like traffic cameras, and some of them are located in a strategic location that allows you like to have some resilience. Okay, I may not have anything coming from a satellite, but I know there are a couple of traffic cameras that allow me to benchmark this part of the catchment. You can also have like social media. I think social media is also like something very useful. You have to be careful how you use it, because sometimes you need to double check what they are generating, but that's also a source of data. So I would say like by keeping multiple sources of data and accessing multiple sources of data, you increase your resilience, and so that, yeah, you basically strengthen your resilience to face these events.
And is that accessible at the moment?
What we do in the private sector and support some of our government users is by doing that by ourselves, basically knowing very well when those satellite providers are passing, where that these satellites are passing, checking social media to know what's being generated, knowing what information is coming from aerial imagery providers. So having a very good idea of different sources, knowing when they are going to sort of monitor our area of interest, and checking that data so that the final user don't have to do that manually, but just like getting a final product that already takes into account multiple sources.
Anthony and Craig, it struck me that you must have very strong international collaboration to build your models, etc. Do you want to say something about that?
Sure. So, I mean, internationally, I mentioned during my presentation that there's a lot of work that goes into coordinating global observing systems. The same thing happens with the coordination of communication mechanisms. So, for example, all of the Bureau of Meteorology weather stations that operate, all of that data in real time goes into kind of a global cache, and then is then accessible to all of the other member countries, all 193 WMO members. And the satellite data, similarly, the satellite operators will ensure that there's mechanisms available, robust mechanisms to enable their members to access that, sometimes via the internet, sometimes via direct broadcast. The Bureau itself does a lot of work in terms of having robust communications as well. So, for example, the radars that are around the country, the 60 plus weather radars, will have copper, wire or fibre coming back to HQ, but we'll also have redundant satellite comms to ensure that that the data continues to flow, because one of the first things, as Sue mentioned, one of the first things to go during a flood event is comms.
Any other questions?
I have a quick one. Sue, thank you very much. I know how all your forces are mobilized when there are critical events like that in Australia, being floods or fire. My question is, there is a lot of space-based application available out there to try to support you during these events, making sure that you can risk and you can address where you have to go, what is the most important, most critical place to go. How do you keep aware and informed of these services that exist? Do you do some engagement with industry? Do you go through NEMA? How all the people who are developing solutions that could help and support you, how can they make you aware of their services? And how do you keep informed of what's out there?
Thanks very much for that question. That is a good question. NEMA is probably the main source for us. They have just established a GIS capability within their organisation, which is now starting to feed us some of that sort of ongoing development information. Me personally, my planning team are trying really hard to engage with organisations as much as we can and getting as much training as we can to try and understand what we can use. It is really difficult because there are so many rabbit holes and different things that we can look at. So it is very hard to try and work out exactly which one to look at. I know that in the North Queensland event, we had some issues. Sorry, no, it was the Western Queensland event. We were told about an aircraft that was flying, saw this huge body of water that we could not identify on any of our maps. We had to do a significant amount of research at the time, digging through. It actually ended up going through the BOM and asking them for their sources, and they were able to provide us a NASA feed that had a satellite image of the body of water that they were talking about, because there were no gauges in this area above Longreach, and it literally was a huge body of water that just didn't come up anywhere. So I think it is super important that we have those conversations. I believe it's about communicating within my planning team and trying to get out there and make sure we have that training. But if anybody here has some ideas or how to make that better, I would love to hear them.
I think we have time for one or two more questions.
Hello, I'd like to thank the panel. Excellent presentation. This is for Sue, but anyone can answer this. You mentioned the grey nomads, and there's plenty of those people out there, and you're having trouble pushing some of this emergency management information via a satellite to them. Can you explain that? I'm trying to, I mean, they're not all driving around with Starlink minis on their roof. So can you explain what you mean by that? Thanks.
An extraordinary number of them do. And even the ones, what we're finding is more and more they are going towards that Starlink type device that they're taking with them. And in the current format, we cannot provide any warning systems to go into that communication device. But yes, you're right, it's not all of them, but we're finding that it's more and more. And what, I think it was Roma was one of the places that had a particular problem, that one of the campsites that they use for the, particularly for grey nomads, is quite a distance out of town. And what they generally find happens is there's no telephone communication out there. They all have Starlink, or at least someone has Starlink, and then they all connect to each other. Like it's like a little community out there. It is also somewhere that floods. So they're trying to work out how do we provide communication to that area or to that group of people when it comes to warnings, because at the moment we can't tell who's there. Like it's not like a telephone where we can kind of ping and work out how many people are in that location. At the moment we don't have an ability to decide where and when these people have got positions. Does that make sense?
So,
yeah, absolutely. We definitely put things out onto social media, but what we find is because they're not locals, they're not generally in the local area's Facebook page, which is where an emergency alert or a warning might be put out for that particular community, will only go to the Facebook community groups, and the grey nomads in particular aren't in those groups. They'll be on a general, travelling group, and we'll still send out warnings where we can to some of those groups, but it's just not targeted, which is a big problem for us.
sorry, can I just interrupt and say that the SmartSat CRC is actually working on some technology that will allow two-way communication between individuals using a small rooftop box or something that would sit on top of your vehicle, that would not only allow the emergency services to send warnings to them, but would allow them to talk to the emergency services. We presented it at the last AFAC conference as a poster. It's called InfoBuddy. We can have a chat about that afterwards if you would like, Sue. Thank you. Any other questions?
Peter Kerr, SmartSat CRC. It's a related theme, but more about the weather forecasting, so for maybe Anthony or Craig. But you talked about the 17 satellites and the 20 sensors that are all seem to be civil spacecraft, government owned. There's a huge interest in commercial spacecraft for doing observations like Spire and Tomorrow Eye. So my question is, when do you see them coming into the kind of WMO mix of data sources? And a second question, if I may, is if there were gaps in information, how do you send a demand signal to industry about those gaps so they might be able to solve a problem using existing or new commercial satellites?
Yeah, thanks. So firstly, on the commercial side, this has been something that's been growing over the last decade, let's say, and Spire, you mentioned, Geo-Optics are another one where they're providing global GPS radio occultation observations. So they're using essentially parasiting off the GPS network to provide weather observations in the upper atmosphere. These have already found their way into the global system. So NOAA in the US has done a global purchase of Spire data, and I think Geo-Optics as well. EUMETSAT, who act on behalf of the European countries, have also done a purchase. They've purchased kind of different data in a way, so it's complementary, and they're each sharing it with one another. It does, the commercial, I think the commercial weather data is a really challenging area. I talked about the Bureau being a global producing centre. It runs a supercomputer. There's actually only 12 countries that have the capacity to run these supercomputers and run the models. Because it's not just running the models, you've got to have a team of scientists and physicists and programmers who are looking after all of this stuff. So there's 12 countries that can do that. So that means for someone like Spire, there's 12 customers for your data. So it's a pretty small market. Tomorrow IO also are moving into, they've got microwave instruments, and they've also got weather radar from space, which is a really exciting capability for particularly those areas like Sue mentioned of Australia, where we don't have any instruments, we don't have any means of knowing what's happening. But the market's tricky. You're dealing with governments who have constrained budgets. And for the Bureau of Meteorology, as an example, I can speak as an ex-Bureau employee. The observation budget is always under pressure. It's always difficult to maintain 60 plus weather radars, 1,000 automatic weather stations, etc., etc. And so, if you're buying commercial satellite data, that's at the expense of something else generally. So it's kind of how do you cut the pie? And I think the challenge, if I can talk about Tomorrow IO and particularly radar from space, the challenge for them, I think, is that countries like Australia and most of Europe and the US, developed countries, have invested a lot in terrestrial-based weather radars, and these are long-lived assets, 30-year assets, and so there's a huge sunk cost there and a cost of maintaining those. The places where we need space-based weather radar observations, let's say the Pacific or developing countries where they can't afford a weather radar network, they also can't afford to buy the data from Tomorrow IO. So it's an interesting area that's continuing to kind of evolve. Thanks.
So I'm afraid we have to call a halt there to all the questions. I would really like to thank the panel for making the effort to turn up today. It was an absolutely excellent panel. I thoroughly enjoyed being part of it, and thank you very much. So everybody join me in thanking the panel.